Hello. Can someone hear me? Hello.
Good evening, madam. I'm Salraj, madam. Good evening.
Yeah, hello, sir.
Good evening. Hello, madam. Hello, madam. Good evening. Welcome, madam.
Thank you.
Yeah. Very glad to meet you today, and we are very eager to hear your talk. Thank you so much for accepting our invitation. Yeah.
It's my pleasure, sir. I am also looking forward to meet only the group of engineers, and that too coming from manufacturing sector. So I am also equally excited to address.
Thank you so much. Thank you so much. We are BHL is mainly manufacturing. We are from subcritical to supercritical. We are also the research stage of advanced supercritical also.
Okay, great.
And we started in 60s with 60 megawatt. Today we are 800,000 megawatt sets. We are already government of India has pumped about more than 2,000 crores to do research on advanced ultra supercritical boilers in par with the.
Wow, that's really nice.
Nice, madam. Do you want to share your screen and check, madam?
Yes, sure.
Yeah. Already sharing rights is given to you. Just check it.
Okay.
Yeah, it has come, madam. It has come. Yeah.
Okay.
No problem. By 5:35 we'll start, madam. People will join at 5:30. We'll wait for 5 minutes. 5:35 we'll start, madam.
Okay, fine.
Thank you, madam. You can sometime. Thank you.
Okay, thanks.
Okay, thank you. Nice. Good evening to everyone. We'll start at 5:35.
எப்படி இருக்கு? ரொம்ப நாள் ஆச்சு பார்த்து. நல்லா இருக்கு. ரொம்ப நாள் ஆச்சு உனக்கு பார்த்து.
Hello, Celebrate sir. Good evening.
Sir, good evening, sir. Good evening, sir. Good evening. Welcome, sir.
Shiv Bhajan.
Madam, good evening, madam. Madam, Dr. Sheila Siddhafa.
Yes, sir. Very good
Yes,
evening.
we'll start the program, madam. 35. So others let them join. Other people let them join.
Sure, sure.
Okay, we'll start the program.
Okay, great.
Okay, there is some introduction and all there. Just I'll introduce you, and after that we will proceed. You can looking forward to hear your program.
Yeah.
Okay.
Yeah,
Yeah,
sure.
we will start the program. Happy good evening to everyone. Today we have an interesting topic, that is manufacturing process inspection, that is going to be delivered by an eminent personality, Dr. Sheila Siddhafa, Principal Data Scientist, Data and AI Service Unit, Cantrell, Bangalore. She is one of the top 10 data scientists in India. It is being told by 2020 by the Analytics India magazine. She is also one of the top 10 women technology leaders. It was also told by 2021 by the Reva University, Bangalore. And she is also one of the top 150 AI leaders and influencers in 2021 by 3A. So first of all, we Institute of Engineers, Tiruchirappalli Local Center with the 7 other participating professional institutions. Thank you for accepting our invitation to deliver a talk in this emerging technology to our members. We welcome you, madam, for our program.
Thank you, sir.
Data is the oil for the IT industry, and data is ruling the IT industry. In today's context, that is, data is important for Industry 4, smart manufacturing, and to decide various important decisions. We, Institute of Engineers, Tiruchirappalli Local Center, conduct weekly technical program for the past 3 decades on every Tuesday. Before the pandemic, it was in physical mode. We conducted in Dr. APJ Abdul Kalam Hall. AC Hall, situated in DHL campus, 3,000 acres campus, and we have an office there. We have an AC lecture hall about 100 seating capacity, 300 seating capacity, auditorium is there, library about 4,000 books. This is our aim is to propagate the emerging technology and latest technologies to members, students, faculties, industry experts, and to the public at the large. After the pandemic, we switched over to the virtual mode. Today is 137th program in virtual mode. So this is about our Institute of Engineers. We regularly conduct workshops, seminars, and conferences, international conferences, conventions, and all. Not only that, we stand as a role model to our professional institutions, situated more than 10 professional institutions housed in our DHL 3,000 acres campus. In that, we regularly conduct programs. This is a role model too, and also we jointly do a lot of programs. We also join with the Computer Society of India, Indian Welding Society, Southern Zone, Indian Institute of Welding, Tiruchirappalli branch, Indian Institute of Metals, Indian Institute of Industrial Engineering, then Indian Institute of Metals, like that, Kumari Arivel Karavai, those all joined with us today. So with this brief introduction, I call upon Engineer Madhuramani, Chairman, Indian Institute of Industrial Engineering, Tiruchirappalli chapter, to introduce Dr. Sheila Siddhafa to the audience. Over to Mr. Madhuramani, Engineer Madhuramani.
Thank you, sir.
Yes, sir, please.
Good evening to everybody. On behalf of Indian Institute of Industrial Engineering, Tiruchirappalli chapter, and other fellow institutions who are taking part in this valuable program, I am introducing the speaker, Dr. Sheila Siddhafa. With over 15 years of industry experience in the field of data science, Dr. Sheila has addressed business problems in domains like Industry 4.0, manufacturing, healthcare, smart city, etc., and provided innovative machine learning solutions. She built a team of data scientists, big architects, visualization, and project management for enabling end-to-end solutions. Prior to joining Cantrell, Dr. Sheila worked as an expert in data science of Bosch. She worked as senior research scientist and scientist at the research center of Infosys and General Motors, respectively. Dr. Sheila received her engineering degree during 2000 from RVCE, Bangalore. She got her MS during 2002 and PhD during 2006 from University of Texas at Arlington, USA, with majors in machine learning and optimization. Dr. Sheila is recognized as one of the top 10 scientists in India during 2020 by the Analytics India magazine, as one of the top 10 women technology leaders during 2021 by the Reva University, along with TerraLogic, as one of the top 15 artificial intelligence leaders and influencers during 2021 by 3AI. She is the associate editor for Inter Science, an international journal of big data management. She is an advisor in the board member. She is an advisory board member of data science program at multiple institutions like IIT Roorkee, Times Group India, PSG Institute of Technology Coimbatore, SSN Institute Chennai, Jain University Bangalore, etc. She received Tool Method Invention Award, Best Poster Award, and the International Best Speaker Award, and many more for her innovative and novel work. She has filed 4 patents and has more than 25 international journal and conference publications to her credit. Dr. Sheila is a member of various societies like Confederation of Indian Industry, Alpha Pimo, Institute of Industrial Engineers, NASCOM, Informs, etc. She is very active in multiple forums, summit, conference, international events, etc., and provided talks as invited speaker, keynote address, and chief guest. With so much rich experience, we are having a wonderful speaker today. So we are happy to hear your talk, madam. I'm handing over the session to Selvaraj.
Thank you, Mr. Engineer Madurai for this excellent introduction of today's speaker. Now over to madam for your delivery, madam. We are expecting. Thank you, madam. Please
thank you so much. Okay, let me get started. Let me share the screen.
No, it has come, madam. You have to make it full screen, madam. This one. Oh, okay, thank you. Yeah, please.
So the full screen is visible, correct?
Yeah, now it's not there. It just again, it came and gone out.
Oh, okay.
Now it has come. Yeah, now again it has come. Yeah, now it has come. You have to make it full screen. Yeah.
Okay.
Thank you, madam. It has come full screen, madam.
Okay.
So you can go ahead.
Okay. First of all, this is a very unique forum for me because, and more affectionate forum, more because it's all filled with engineers, and more close to heart is a manufacturing domain. So being an industrial engineer, this of course feels very nice to address this wonderful gathering. From a domain perspective, I might not be as great as a gathering here, but would love to have a more discussion-oriented engagement at the end of the session. So with this, more from a artificial intelligence perspective, I'll just give you an idea of what people are actually doing today, or in other words, how the solutions are versus how different are we developing the solutions, and how do you see this getting embraced in the manufacturing sector. So that's kind of a sorry, anybody had any questions or something to say?
You can proceed, madam.
Okay.
Yeah. Okay.
Yeah. So the moment we say inspection or monitoring, so basically we are just checking what is going on. And today we all understand that it has gone from manual mode to automated mode. Automation does not mean that we'll allow robots to do this job. So of course, data science by itself in its own way is able to do the automation. So before we go to the actual production part of it, let's understand how the monitoring has taken place in the past and what is it actually doing. And then we will go to the true inspection. So today, in terms of monitoring the activities or mission more specifically, this is what is called as condition monitoring. Most of you might be aware of this. Okay. So whether it is such a complicated mission or a simple mission, today in the name of digital twin or in the name of IoT, people want to monitor most of the parameters that are there and then understand how things are working. Okay. So you name a sensor, more or less they would have mounted on the complicated equipment for that matter, and they collect real-time data. So per second, fraction of a second, you will start getting this data, and finally, the whole idea is to find out if something is not normal. Okay, so basically, what they will do is they will create one threshold, and say if it is going anywhere above or too below this, then it is breaching, and thereby this is an anomaly. Okay, this is all what you all already know. Now let's see what really happens. Okay, now in real life, if you talk about a given equipment, and say this is the total on your x-axis, you find the new to the end, so total lifespan. So, and if we want to draw, just a theoretical plot on the life performance of a machine. So it will be very good in the very beginning of this, and as the time goes by, it will start deteriorating. This is kind of known. So I've just drawn one very simple curve here to indicate the same thing. Now, when the machine is performing really good to performing very bad, also very closer to the end of its life, the idea of this digital twin is to capture data. Okay, keep mounting these sensors and capturing data. If we ask a very fundamental question here, do we need all the sensors? I mean, all in the sense, I don't mean to say all 100 sensors. And typically, they will say temperature, flow rate, pressure, and so on and so on, vibration sensor, and all these sensors they will mount, right? So the question is, do we need all these sensors? More specifically, at all the time. So even if the machine is new, do we need it? Why? I mean, the question is, why do we need all these things, whether the machine is new or at the rear end of its life? It would be more like, taking this very young man who is very healthy, who is more energetic, and saying that, there is a possibility of something happening to you. You never know. Things are very uncertain. So thereby, I will start monitoring you. And, we will shave his head, and then we'll start mounting all sensors on his head and start monitoring the mental health and the brain activities and so on. If we do this, do you think he's going to like it? I mean, whether a man or a woman, nobody likes. We know how much we spend on, the saloon. So, so nobody wants to go around with these sensors. That is true. Similar case with the, limbs or the arms. If we say, no, we really need to monitor whether you are performing well. Are you feeling very weak, tired? And more so, I mean, heart is very important. So we'll start putting these sensors throughout, and we will monitor day in and day out for you. We will not like it anyways. Even though it is very crucial, and we know that health is more important, even then we do not want these sensors to be mounted on us. And even today, the vitals are captured in the healthcare scenario very often only in this case, when, more or less, the person is in a very, very critical ICU condition. That's when you will see more sensors and not the human being. Okay, that's what it will land up in. But we do not want to land up in such a scenario, but at the same time monitor. So what does that mean is, when the performance of the machine is deteriorating in this direction, then the way the type of sensors we have to mount at different instances or capture different kinds of machine related information would also be something very limited, as the machine is very new. And as it goes to the rear end of its life, it can increase. So thereby, of course, what is more important is to know which sensors to mount where, when, and capture only those. Sometimes even just the machine related information itself is more than enough. We may or may not even need sensors at times to monitor how the machine is performing. Okay, so we can let go some of the things and not monitor so much for that matter, and keep only the ones that are essential depending on what stage the machine is at, and monitor them. Okay, so now once we know what to capture when, then we know we have already dramatically reduced the volume of data that we are collecting. One of the challenges today most of the leaders are mentioning is that they have captured so much data that storing the data or maintaining the data itself has become very, very expensive for them. Forget of the fact that, they are extracting information out of that data and analyzing and consuming. That is not even done for most of the data that they have captured. So thereby, you can understand that now we have reached more or less a phase where almost from no data capturing all the way to capturing so much data that, that itself has become so much of a burden. Okay, so we do not want to do that exercise. We want to capture only instances when we need and how much ever we need. That's all. Okay, and there are also many of the startups who are providing solutions to manufacturing sector more precisely. I have heard at events like NASCOM and others that they have, most of the industry people are questioning, now if you're collecting per second data, what is the return on investment that you're going to give back to us? That means to say, if I'm collecting this data, what is the operational benefit that I have? And most of them are not able to give the justification, which clearly means asking the very valid question of why are we even collecting so much data? Okay, very truly, we do not want to do that. Okay, and just collecting whatever data when we need has made a lot of difference. Of course, in terms of hardware, infrastructure, analysis, in every aspect for that matter, it has, of course, done a wonderful job. And see, even if they collect, say, 100 parameters data and keep collecting this on and often and keep, giving this information, finally, when you look at the data science model, it does not have so many parameters into the solution that it is building into its algorithm. Very limited, only very influential parameters only are there. Then why did we capture so many parameters? Sometimes in some of the manufacturing sectors, especially in wheel manufacturing companies or tire manufacturing companies, we have seen that around 3,000 different parameters live are captured. And of the 3,000, if we say how many of them are actually getting consumed in the model development of the data science, only 20, maximum 30, especially during the casting process, machining process, and so on. So then if that is the case, why don't we share this knowledge and make sure that we do not reiterate this process of asking every wheel manufacturing company to collect 3,000 parameters. Okay, that's one of the ideas here. Then the next thing that we notice is once they capture the sensor data, they start throwing dashboards, and basically the parameters are monitored and it will start showing these. Now these dashboards look wonderful. This is just a sample snapshot that is here. But if you ask the people, are they actually consuming this dashboard? They're like, it is a colorful thing. It is nice to have there. Okay. Very rarely have we noticed people taking the true benefit of the dashboard. That is because the values are thrown, as I was saying, per second. And whether it is an older machine like this or a complicated machine, a sophisticated machine like these, we don't, if we look at them, they don't fail every hour. They don't fail every day. They don't fail every week, every month. Maybe once in 3 months or once in 6 months, if at all, there could be any kind of a performance issue, or there might be a failure. Some of the equipments don't even fail for 1 or 2 years. Then why are we collecting data per second? Okay, good. So then you might ask, then how often do we need to collect? Is the question. So what should be the frequency of data collection? If we start thinking, should we collect them once per month? Maybe hourly, maybe 30 minutes, or maybe on a uniform note. So should it be like consistently like 30 minutes, every 30 minutes, uniform? So if you start digging deep into this, you really are kind of puzzled. It's very confusing to know how often do we need to collect the data. Okay, so maybe you can say that, initially I will have a very high frequency of collecting data. Then with time I will reduce, and then it can increase. Okay, that is also one thought process. Somebody would say, no, initially it will be very low. That means when the equipment is new, I will have a very low frequency of data collection. Then I will bump it up, and then as it is anyway dying, then no need to collect data. So then I will actually let go it. So different thoughts will provoke different ways in which different frequency curves that you want to develop data collection. Okay. Some would say, no, normal is the best way. So I will have a long tail at the end. So this is how I will collect. Okay. Now you could keep on arguing and, this works for me, that works for me, and so on and so forth. But finally, if you look at it, it could be a dynamic frequency by itself. So sometimes the frequency of collection could be more, and sometimes it could be lean, depending on what exactly the machine is going through. Okay. It could be a very dynamic frequency, because we as human beings, if we do an analogy, not that there could be an year full where we do not monitor any of the vital parameters, but then there could be another 1 or 2 months where we monitor it so often, and things like that. Okay, so we can stick to the same logic. Finally, at the end of it, again, we'll come back to this condition monitoring, where, after we have collected the data at, say, for example, 1 instance per day, that's all. Even though the machine is working for 24 hours, we just collect 1 instance, and then the following instance maybe 1 day later, and so on. So whatever be the frequency, we collect only from the required sensors. And finally, we have to still go ahead and say, whenever there is an anomaly, to throw alerts. Okay. Now, once we do this, say with all this circus, we have now given a wonderful, as required, very efficient, cost-effective solution. Okay. Now let's go ahead and see what really happened once we gave this solution. Okay. So say this is a very complex equipment that was monitored. Only the vitals, very, very important ones, very cost-effective way. And the moment we throw there is an anomaly in this, the expectation is the technician is going to come running, because the equipment needs attention over here. Okay. So the moment the technician comes running, our data scientist would give this plot which says, see here, I have monitored parameter number 10, and it says, there is an anomalous behavior here. So see, I'm even feeding you this wonderful information. So now go ahead and fix it. Okay. So from a data science angle, it sounds very wonderful. We have done our job. But when we look at the technician, he would be all the more puzzled. He will be puzzled more because the equipment is still working, and we are throwing alerts in advance, and he does not know what to fix. Now, the good thing is the technician only knows by the symptoms. Only if it had stopped working, it is making a lot of noise, if it's going slow, if it's got stuck, only then he knows to repair it. Now, looking at the signal, he has not studied this language at all. So how is he going to connect the parameter signal that we have derived with respect to that of the equipment or the components? So that is where most of the condition monitoring things, digital twin concepts, which were developed and stopped at the condition monitoring phase with the anomalous detection, has actually, if you stop right there, it will be of no actionable benefit to the industry. So what we do is we go one step forward, and we also help in identifying which is that component which precisely needs a maintenance or attention, which could be repair, replace, whatsoever it is. Okay. And in order to do that, what we do is we understand the relationship between whatever, say we have captured 10 sensor data or 10 parameters information from the equipment. So that anomalous behavior is mapped to the corresponding component. The mapping could be 1 to many, many to 1. Okay. But we still go ahead and extract what could be the ones which need attention. Okay. Great. So now we have kind of helped this technician to know that the moment you see this parameter out of control, then we are not going to give him any of the signal information. That means I'm not going to give him any plots. I'm going to directly tell him what components need attention. Okay, good. So now do you think he's happy? Well, what he does not know is, okay, it needs attention, but what kind of an attention? What do I need to do there is still a question mark, because it is still working there for him. Okay. So what we do is the next step, we help him in guiding, and we provide recommendations to say, what is the next action that he needs to check and work on. Okay. So a very detailed guidelines is also provided depending on which component and what actions needs to go in place. This, of course, requires a lot of history information in terms of, okay, this is the component, what are the type of fixes that are there. If it's the next component, what are the type of fixes that are available. So based on that, a recommendation is provided. Now you will see that the technician is all happy because he now not only arrives there wherever the equipment is, but he also knows what he needs to be doing. Okay, so that's the kind of spoon feeding that's going to help him fix the kind of issues that are seen in advance. We do not stop our journey there. We want to go ahead and do the job scheduling on the machine so that the machines are utilized in a very nice manner. What we have noticed is some casting machines, for example, are heavily used and some of them are leanly used for whatever reason. So thereby, if there is no equal balancing of the stress level or the load level on different equipments, we can see that some of them do underperform and some of them overperform, or the stress load increases and thereby the health is also gone for a toss. So what we do is also help them balance the workload depending on how efficient the equipments are, and so that we are not only trying to see that, while we're monitoring and giving the maintenance information, we are also seeing if we can reduce the amount of maintenance that comes out or this particular equipment needs. Now, with this, one of the use cases is kind of what I wanted to talk. I would love to now hear if there are any questions on this before I move on to the next story or the use case. Any questions?
Participants, madam is asking, has given session for the questions. Any doubt, anything, whatever presented, you can ask now.
You can proceed, madam.
Yes, sir. So you're suggesting that I just continue and there are no questions from this? Or I mean, just wanted to hear, because you are seeing most of the equipments very closely. So do you really think that this kind of a solutions are going to make any difference? What is your feedback is also something that would be nice to hear as well.
Yeah, it was a very good start, madam. They had a basic to understand the concepts which started, what is maintenance, how it's be addressed and all. It was a very good starting session, madam. Thank you, madam. Thank you.
Oh, okay. So anyway, I was just talking about the solutions. If you have seen anything implemented within your organization, your industry, and if you have seen any progress in this dimension, so how do you see standing there or getting such kind of a solutions integrated into your company? So that's where I was looking at.
Thank you, madam. You can proceed further. We'll keep the questions at the end, madam.
Okay.
Please. Thank you. Please.
Okay. So let me now move on to the next use case. This is something very common that most of you might have heard or seen such things. So which is where the true inspection of the product that is manufactured takes place. So typically, if you're talking about a tire manufacturing company, we notice that if there are 50 people involved in the production, 100 people are actually doing only the inspection part of it. So double the number of people are actually involved in the inspection. And that's a little tedious activity as well. So you're aware that there are data science solutions which are more of visual quality based. That means just mounting the camera, taking the images, and the algorithm is able to do the inspection on behalf of human beings. So this is something that you have noticed, but I would be going through a journey which is kind of different from the normal. So when visual inspections are going on, so say this is a conveyor belt and there are products going on the conveyor belt, which is a completed product for that matter. So the idea is to mount the camera in such a position that maybe one or more cameras for that matter to capture different angles of the object and take pictures to be able to say whether it is a good or a bad. But in order to do that, we need the images to be taken, which is actually data for us, and mark wherever there is an anomaly. So say there is a box here. Now, if at all the edges are broken, or if there is a crack, or if there is a dent, then those have to be marked. So because once you mark them and give, that is when the machine learning algorithm or deep learning algorithm is going to understand what is defective and what is non-defective. Okay, so this kind of an annotation or markings on the images are very much essential. And more than, depending on the product, sometimes they ask for even 5,000 images or 10,000 images to be provided to be able to understand the nitty-gritty details and the different types of the defects that are possible. And once the images are all marked and given, so there are a combination of both good images as well as images where there are defective products are also there. Okay. Now, then that goes to the data scientist, where he develops an algorithm on this kind of a data set. So basically, he's going to help in classifying and saying, okay, this is defective, non-defective, and so on, good or bad. And once if we know it's a good product, then it will keep going. On the other hand, if it's a bad product, then it will go into the defective basket. Now, the solution actually typically stops here, but we do not stop the solution here, because see, when we look at the solution, the defective parts come and drop into this basket, we then again expect the domain expert to come here, sit and observe what are the different types of defects that have come in, and find out if that defect is so bad that it has to go into a recycle or it can be fixed. Okay, so this is something which is also done in the domain or in the manufacturing sector. Okay, so thereby, now what we are trying to do is, we do understand that this annotation process, which the subject matter expert is doing, most of them are digital these days, and it's a real pain. And to annotate even 100 images, it would take at least more than a week's time and dedicated time by different people. So thereby, we are thinking, how about we just get rid of this kind of activity? What if we are able to develop an algorithm where we do not need so much prior art of annotation to be done, but the algorithm itself discovers what is defective and what is non-defective? So, and when the algorithm is doing this, we are not even having an on-site data scientist to do this as and when you are sending the data. No, all of this is more or less automatically integrated. The logic that goes on in the brains of a data scientist is embedded into the algorithm so that it knows what to do when, and it is taken care of. So you don't need a data scientist to be sitting there doing all the exercise. Okay, great. So you don't need an annotation, you don't need these things, because our solution is already having all of those logical things that are required. So basically, an artificial intelligence is already embedded in there. And one more important contribution is that when we know that the products are defective, it not only says that it is defective, but it also goes ahead and classifies to the next level, depending on the magnitude of the defect, depending on the intensity of the defect, whether it has to be a scrap, or it is of a defect type 1, or it is of defect type 2. Meaning, it is not just saying that it is defective or not, it is also saying it is crack is the defect, dent is the defect. Okay, that also some of the algorithms would do. But what we are doing over and above that is, there are products which could have more than one type of a defect. So there could be a crack along with a small hole. So if there are more than one, that is also something that we are discovering, marking it out, finding the magnitude of those defects, and accordingly classifying it as a scrap product or a defective one, which can be fixed. So if it's a crack kind of a defect, and we know what type of a fix it is, so we don't need this person to do this job. So automatically the bucket will be placed accordingly, and the technician is going to come and fix those. Okay, so he knows everything that comes in this bucket will have only a crack type of a defect or only a hole type of a defect, and accordingly the same type of a fix he would have it handy. He will sit there, he's just going to fix them, and then the corrected components will now again go back to the good part section and it's all taken care of. So more or less what you notice here is a complete end-to-end connection and making sure there is actually no manual intervention in between. And the most important value add is, even if you keep changing the type of products that you are manufacturing, it still works good. So then you could ask a question, how are you doing this? How is that your algorithm is able to identify what is good and bad by itself? So there are methods called unsupervised algorithms, and we have adapted the unsupervised algorithms in such a manner that, of course, it's not ready-made that we could just plug and play. We have designed the complete workflow and created the algorithm, which is actually going through the patenting process. And what's happening here is that the entire algorithm is so that if only a data scientist was supposed to sit there and do, it's going to do that job precisely there. Okay, just to give you a sample of how it is done. So now say the first bunch, what you see here is a bunch of images that are there, which are not at all annotated. That means nobody has marked them saying, this is a good image, this is a bad image, or bad in the sense, there are defects on this. Nobody has done those markings. We just have the images. And this happens to be a metal sheet production. So we just feed the data into the algorithm, and then the algorithm is just going to automatically classify them as good ones and defective ones. Now, if you look at how good it is able to do this classification, we are more than 90% accurate in doing this classification. Okay, the moment I say we are 90%, then you say, oh, still 10% we are not good. Very valid question. But this is all going on in the background. So this work that we are doing is in the background. And when it comes to real time, I will come to that, how we do in the real time part of it. So in the history of things that are that you have already manufactured, we have taken the images and then we have actually bifurcated into good and bad. Now what we do is we take the defective group of images by itself, and within that defective, we will go ahead and assume that as though this is the first set of images that have come to us, like this kind of an image, and then we'll go ahead and reclassify them. And that's where we are using clustering algorithms to do this. So when we redo that, then what's going to happen? We will be able to again get another chain. It's more like a hierarchical tree approach. So we will get again another good one and maybe a bad defective parts kind of a group. Now what happens is you could say that the one which has been classified as good from this might also have defective products, but I do not care. What I care about is only the defective parts here, which I know for sure will be 100% defective in those images. Okay, and there we'll end up getting 100% accuracy, and that is the image that I'm going to use for training purpose to eventually do this activity on a real time. So that's where you see the second level of clustering. And here now, once we have that very core set of images which we know for sure are defective, we take those images. So this is that bunch of images, and then we try to cluster them again. Now, when we do this clustering, it gets bucketed into different types of clusters by itself. So that means all the cracks will come together, all the dents will come together, all the scratches will come together, and so on. So this by itself grouping will occur by itself. And again, here we will do a regrouping just to ensure that the learning that we are getting from this is 100% correct. Okay, so we will not stick with the 80. We are going to regroup until we know that even if the number of defective sample data is minimal, that is still fine, but we want to make sure we get the true ones. Okay, so that is how we are able to generate the data ourselves without having the need for any annotation. And the algorithm, the kind of hierarchy approach that we are using, that's going to do its magic in terms of how the data scientist is going to bring up a very wonderful algorithm. So that's kind of embedded here. Okay. Now, coming to the aspect of coming to the aspect of detecting not only one defect on the image, but also more than one defect. Okay, so what we do here is that we are in a position, so given the first image that you see here, we want to go ahead and discover where exactly the defect is. So we have gone step by step to, and see, initially we thought this whole thing itself, we created a bounding box around this, that the image itself was covering the defect completely. But slowly we have been able to narrow it down very close to the defective area by itself. And if you want to make it a little more bigger, that's where we will land up in saying, this is the bounding box around the defective piece only. So we have been able to narrow and get very closer to where the defective piece has been through multiple iterations from a deep learning perspective. Okay. We not only did so when we are going and doing identification of the defects from each cluster and marking the bounding box. So you can see that if they are at multiple places within, so it's not only at one place, if there are at multiple points also, we are able to discover them. What we also tried doing was, if there are parts, say for example, there is one hole here, which is a normal thing to be there. So our algorithm should not go ahead and detect that particular hole as a defect. So what we do is we use the reference of a good part that we initially classified as a reference to know that, okay, if it is like this, then it is normal. Anything other than that could be a defective one. So thereby you can notice that it has not marked these holes as defectives, but anything other than that as defective ones. So by the end of this journey, we are not only knowing that if there is a defect, but we also know where exactly is the defect, how big is the defect, what is the defect, and thereby what is the action to be taken as well. Okay. Any questions so far before I go to the monitoring aspect? Somebody has in manufacturing. No.
Actually, ma'am, if the product if the defect is visible too easily, then we can do the same. But some products like tube in company, they should check with the non-destructive test NDT. Like that material, how to we can separate whether single defect or multiple defect, whether the problem can be done by simple process, whether it is going to scrap like this.
Very, very, very good question there. So in terms of saying, okay, if it is not visible to the eyes, okay, and if it is a very complex scenario, or for example, pipes is also what they were mentioning about. So excellent question over here. In terms of how do we discover defects if they are very intricate or so let's so what we have done here is in such scenarios, especially from a monitoring the equipment or the need of a maintenance. So that's where I can say what we have done is not precisely the tube, but it's a huge pipe for that matter. And the dimension of the pipe is really huge. We have sent a drone inside the pipe, which will take the picture. So sometimes we allow it to take the video as it goes through the pipe, inside the pipe, and then it's actually collecting images inside that huge pipe that's there, or the tube. And then we are able to real-time convert that video into images and say whether there are any kind of abnormalities on the inner surface of the tubes. That's one thing. Second is if they are at a very great height and, and they where we cannot reach. So it's not really on a production zone, but say there are anything on a windmill. Is the blade having any kind of a damage? Why is it not rotating well, and things like that. So that's again where we send a drone to capture the images and then come back and see. We have done this exercise also where there are people who are going into some very remote areas, trying to fix some things and come back. So that's when, again, we are either having an edge device that's going to capture what this person is doing and guide him whether the operations that he's performing on that particular equipment or a machine is correct or incorrect, or the process is correct or incorrect. So that's what we are doing. Coming to places which are not kind of accessible for the vision as such. Now, on the other hand, if you are looking at welding operations for that matter, where, once the weld is done, you cannot see whether the weld was done correctly or incorrectly. That means to say there could be pores in the weld, which could be so much that, the big pores that, the weld is not that great. Okay. So here we are coming up with an approach where we are working with one of the IITs, and we have developed a solution where when the welding operation is going on, we have only a sound sensor. A sound sensor is very negligibly cheap in terms of the cost perspective. So a sound is captured when the welding operation is going on, and just hearing out the sound, we are able to say if there is any kind of a defect in that location, yes or no. Okay, and the magnitude of the defect is also something that we are able to estimate. That will come in. So something which is not on the surface, but internal to a product. Okay. So that's where this typically on a welding operation. So there are defects which are internal. I mean, if you start trying to find out where it is, then you'll have to literally break the welding, or there is a CT scan machine which is used, so which is even more expensive. So thereby, instead of doing this 100% inspection either through a CT scan, a scanning approach, or breaking the weld, or the load test for that matter, which typically companies would do, we are using just a sound sensor, and we are able to locate where the defect could be. And so that any kind of, so all they are going to do is just a corrective action during that, in that area. And then we know that it's going to be much better than not doing that kind of a fix. So that is one exercise that we are doing where the defects could be internal as well. I hope that answered your question, sir.
Okay, ma'am. Thank you, ma'am.
Okay. I saw some note on the chat. So good start with the intro. So even though a few hundred data are useful in maintenance, other data may be useful in the long run. Very truly mentioned, sir. So that was the whole note. When people started collecting data, they wanted to store and maintain it because they feel that there could be some other objective problem that we would want to solve, and it will come in very handy at that point of time. Now, see, even before 2000, okay, the year 2000, pretty much there was no sound of IoT and so much of collection of data and the need. Industries did exist that time. They were doing good. Now also they exist. But now they are way better. Now the standard of doing the operations is way better than what was going on 20 years back. Well accepted. If we at least have an infrastructure, we know the approach, how do we collect the data, when do we need to collect the data, and so on. Now, if we start storing the data, thinking one fine day, I'm going to say, even 2 years down the line, okay, 2 years down the line, I'm going to define another objective for which this data is going to come in handy. Now, I am a little, thinking twice on this, more because, see, we also have this notion, something that was 20 years back is not true today. Something that was true 2 years back is also not true today. The scenarios that the equipment or the product went through 2 years back is very different from what is going on today. So do we really need to capture and hold that much data for so many years? Because if I define a new problem statement today, and I want to solve that, and if I need some data, it takes hardly any time to capture the data because I already have the entire infrastructure in place. I already have the sensors in place. Now, it's just that I have to increase the frequency of my data collection. It's no big deal. So I would say the farther behind you go in terms of collecting the data, history data is less meaningful at this time. So thereby, collect the data only when you need, because now you have a complete framework that you need or you want to. So if you keep on stacking, one fine day you're going to get so overloaded that you will start playing only with your infrastructure cost. Your down payment maintenance month on month the bill is going to really shoot up. So thereby do it when you need, because now at least it's absolutely no problem to collect the data. So is that okay? Or I'm open to discussing if you see it the other way around, sir.
Good evening. See, we need to have more data for doing our reliability engineering activities. So you collect data, it is only a present data, but we need to know what would happen. So for reliability, we need to have past data, and for your information, we collect and keep 25 years data.
So do you respect that 25 years back data as equally as this year's data, sir?
Yeah, when we do RAM analysis and when we do HACCP analysis, we use data first from that one. Okay. So before we say that, before we conclude with our SIL analysis for a heavy pipeline, etc., we need data.
So for the last 25 years, nothing has been changed. That means whether the legacy machines that were used versus the latest equipment that you're doing, the manufacturing process, etc., is it just the same that you can rely on your old data as much?
See, the failure pattern changes. It won't be like, constant. Correct. So we need to know what type of failure we had once upon a time. From that onwards, we have to do it. That is how, we will be able to, eliminate risk.
Very nice point here, sir. So this is where we believe that instead of capturing per second data and storing it for 10, 15 years, we capture the summary information of the attention needed information only. So that's the approach that we are going by. So say, for example, only 10% of the products are defective and 90% of them are good, or the operations of the equipment are good 95% of the time and only 5% of the time it has been not performing that well. So there is a summary version of this 95% of the time that it has performed well. And only that small amount of data we capture, which is a representative of the entire year's data. So that we do not load ourselves, because that entire information is collected over there and we also understand what is the frequency over it. Same story with respect to any other aspect. More of a statistical information is good enough to capture the gist of it. So that's the new trend that is coming up, because the cost of handling the data, analyzing and reworking when compared to what it's actually doing is already reversing. So that gear is already, reverse gear has already started. So that's the latest trend that we are noticing in terms of, can we just take the information? Because even if you have bunch of images, then finally somebody has to extract and give a small report out of it. So that is already available.
No, see, the concise report it's with reference to a scenario, but failure pattern may have a similar scenario if you have a similar operating context. So failure pattern we should have, and failure mode also we should have, and they are to be recorded.
Correct. Okay. I am with you, sir. So all the failure aspects are maintained, but typically the good operating conditions are much more than the bad operating conditions or the failure cases. Failure cases in the lifetime of an equipment or the production is very small when compared to the very fruitful time. So thereby we are reducing the fruitful time information, but we are having the defective information or the failure kind of an information loaded with wealth. So that we are capturing and holding, not really the 90% of the time when things are going good. So that's how we are able to, minimize the effort that we are putting in terms of the data.
Yeah, it's okay. Yeah, it's fine.
Okay.
Madam, there is a question of Mr. P.S. Subramaniam, engineer P.S. Subramaniam has his hand. So Mr. P.S. Subramaniam, you want to ask any question, sir? Sir? P.S. Subramaniam, sir? He has raised his hand. Okay, madam, you please proceed, madam. Your presentation is set to there, or madam?
Few more minutes. I mean, am I?
Okay, you go ahead with the presentation.
Okay. So what we then do is we also monitor, how many of the parts are coming to the fixing part of it, the number of defects, and how many units for what type of a defect. Now, once we keep monitoring, and with time, if we notice that his load has increased, that itself is a trigger for us to see there is a need for retraining. So what we have already done now is exactly what sir was saying here, that we monitor the defective parts, not the good ones. So that good ones is a good one, we know that. So only the defective types. So each type of a defect we keep monitoring in terms of how many of them are there, how was the story, say last quarter versus this quarter versus next quarter, or monthly or weekly, and things like that. And once the magnitude has changed in terms of the number or the type and things like that, that's when we give this as an input back to the production unit to say, see, typically you were getting only cracks. Now dents have become more, but the cracks have dramatically reduced. So even if there are ups and downs in the type of defects that are going on, we know that now it is not only time to retrain our model, revisit our model, but also input to the production team to see or get inputs from them back to see if they have made any changes, which is actually reflecting here in a different kind of a defect types. Okay, so then very briefly, I know I'm almost through with the 1 hour slot. So very briefly on the process inspection. When I say process or the production process, so most of the inspections goes on once the part is produced, or it is halfway through, or one part of the work is already done. But what is very minimally noticed is, say there are different kinds of activities that needs to be performed, whether it is manual, semi-manual, or sometimes automated, but typically it works in a case where it is manual or semi-manual. Now, so just take an example of a cutting operation that's going on. So these are all sub processes that go before a final product is there. Now, if at all the first step itself goes wrong, then you go through the second step and all, we all understand it's not only a waste of time and energy, cost, everything is not being efficiently done. So, but very minimal is done in terms of inspecting during the operation itself. That means when the cutting operation itself is going on, did we do the checking to say whether the cutting was performed correctly or incorrectly? Okay. Now, sometimes it is possible. So if it is a semi-manual case, say the sheet, instead of a single sheet, it just got folded while the way it was fed in. So sometimes it just got folded and 2 layers were getting cut at the same time. Okay. If at all this was not noticed, then that kind of replicates for some amount of number of products that that are coming out of the step 1. So for this particular step, what we do is, so say this is a folding activity. So it could be for the airbags in the car or any leather related seat covers and things like that, where folding activity is required, which could be completely manual or semi-manual. So what we do here is, again, we do not ask for a lot of information on how you do. So just one reference video to talk about the correct operation process that is adapted in doing that activity. Okay, so either it's a cutting or a folding. So I've just taken as a folding as an example here. What are the various steps that it has to go through that we extract from the reference video that you have? That's all. Like, even if you're using one video to train your new employees or your trainees, so that is also one reference video. That's more than enough for us to generate the data and identify what are the steps that goes through in this. And the way we do that is, any video is converted into a bunch of images. Now you can see that, the same step could be repeated 100 times, but we extract what are the key tasks only from that. And then we use for comparison on a real-time purpose. I'll just share this. So for simplicity, and to begin with, how we started was, we had one of our employees himself to, start folding a shirt. Okay. So folding a shirt took few seconds. And when he did this activity, and when we took that few seconds video and converted it to a bunch of images, it was around 1,000 different images. Okay. Of course, when we say 1,000 images, there's a lot of repetition. From that, if we actually manually had to understand how many steps were there, these are the 9 steps. If somebody does these, that's correct. And he has to ensure that, the sleeve has not fallen off, and he has done it correctly. So when we did this automated through the learning, that is where we saw that the algorithm is able to derive 12 steps from the entire 1,000 step of a reference video of folding a shirt, and only 3 images happen to be a redundant one. Okay, so thereby we were able to extract the correct tasks that needs to be performed, and in the order. Of course, it's going to come in the same sequential order. Now, for whatever reason, if the sleeve is not folded correctly, or he misses any one of the steps, say step number 6 or 5, he just missed, and he just went on to the next following step, then we give this as an error, that this step we did not find when the activity was performed. Okay, so that is how we started, but eventually we took other sample videos that we could, and say, for example, this is where they're marking and cutting and then actually inserting the screw into the metal piece. So you could see we used 2 different approaches, and the color histogram approach as well as in the edge detection approach, so that even if the background changes, things like that, we are still able to incorporate. And from 3,000 or 4,000 different frames or images that we were able to get, depending on how long the operation was, we are still able to identify the bare minimal number of steps that are there and verify and check whether the operation was performed correctly or incorrectly. That's all I had. I know I've taken 10 minutes more, but yeah, thank you all. And I still look for any questions that you might have.
Thank you, madam. It was a wonderful session. Thank you so much. You shared many thoughts, Ines. Really enjoyed your talk. Thank you so much. I want to ask a doubt, madam. We are boiler manufacturer. We are producing more than 5 to 7 lakh tons of boiler components, various components. It involves visual inspection, ND inspection, other hydro test and all. During this, how do you incorporate all these ND? Actually, we have unit 2 we started for the supercritical boilers, where we do a lot of pressure parts involved. We have got a lot of semi-automatic, automatic machines and all, where the welding is done immediately. Real-time radiography is carried out there. With the operator, they evaluate and tell it's okay or not. Like that, it is almost because we ensure the first line inspection. We first we ensure the joint okay. Then only we start the production every time. Actually, after the Like that, what is it? Camera, how far it can identify the defects. Visual is the first foremost ND method, and followed by the ND to know the subsurface defects, deep defects, radiography, and finding the depth ultrasonics and all. In that aspect, how is it possible to form the line inspection? That can you show some idea on that?
In the boiler case, sir. So
Tubes. Just boiler, we manufacture a lot of tubes. Actually, it carries more than 25% is tubes, pressure parts. That's what.
So the way we still look at it is, if today, if it's a manual operation, so do you see a person actually viewing through the tubes, or how is it done manually today, sir?
No, tubes are manufactured our sister unit, that is seamless tube plant, where we bring it here and do the welding according to our requirements. Whereas various supercater, reheater coils, economizer coils, according to our drawing, we will manufacture it and we will prepare the metal preparation and bring to the process, the production shop. And there we do the welding. We have semi-automatic conveyors and all. Its welding is done, it's being monitored by the real-time radiography, and it's taken to the further welding in a panel processing machine to make the panels and all. In that, we do inspection. We do this first. We do the straight tube put welding, the MIG welding, and we do it real-time radiography. The radiography the operator sees, and if it is okay, it will be sent to the further processing. That is how camera can play. That's what my point is. How camera can play.
Yeah. So if the defect is something seen on top, so even though it's a tube that you are manufacturing, so if it's very thick, then maybe if there are defects on the internal surface and not on the external surface, then it is difficult if the camera is mounted on the top. So that's where one other approach people are also thinking is, if we can have maybe a rod kind of a thing which has mounted some cameras at different instances, and the pipe goes through this device. Because it's hollow inside, right? So it goes, and then the images are captured to check on the internal surface. This is one thing that they are trying to see. As the tube comes out, it actually gets the internal surface view. But that will only help in detecting internal surface defects only. So cameras can go only to an extent which is vision possible. But if it is internal, so the only way we are doing in terms of, say, if the pipes are anything manufactured from a casting operation, or in terms of, after that welding, of course, but machining operation. So typically the idea is, if the parameters when you are doing a casting operation of a tube is so and so, we kind of have an idea whether it's going to produce a good part or a incorrect part, okay, or any defective part for that matter. So this is what we have done actually for a wheel. So wheel is, of course, is very small in size and things like that. So, but any kind of a possible defect, whether it is internal, because after getting the casting out, it actually goes through an X-ray machine or a screening machine for that matter to find out defects. So what we are doing here is monitoring the process parameters, and based on the process parameters, say the possibility of having any kind of a defect, so that the inspection goes on only for those tubes only, so that we don't do 100% inspection for all of them. And that's a very good representation to say only these needs attention. So that if you're doing manual, you could do that. Or if you want an automated way, maybe X-rays or things like that can be done only for those limited ones by a traditional approach. Or you could still use, for a surface part only, you could use a camera. Beyond that, camera is not going to come in very handy.
Thank you, madam. Thank you. Actually, what we have actually up to 76.1 mm OD diameter, we keep it as a tube. Beyond 76.1, we say as pipe. That's what we actually board 600, 700 and all. That is okay. But wall thickness will vary. Up to 76.1, whatever wall thickness, it is, we say as a tube. Beyond 76, we say as a pipe. Okay, please, thank you.
That will be only based on the dimensions, no, sir.
Yeah, okay.
But any defects would be.
Yeah, that is different.
That's another one.
Now the session is open for questions. Our Balasubramanian sir, GM, our chairman is there. Sir? So the session is open for questions. Others can ask.
In the oil and gas,
Yeah.
for doing internal inspection, we call that process called pigging.
Yes, sir. Yes, that's true.
So what you said that you send something and you try to internally inspect. We do it like 200 kilometers or even 1,000 kilometers. We do pigging in steps, and sometimes we travel along with the pipe, and then we have a real-time data, and then we try to locate. It is called pigging.
Yes,
For
sir.
tube, we don't normally have an internal inspection because we believe on eddy current test, at the time of manufacturing, and that tube we select and then use it, and we try to plug and then do a hydro test for the tubes.
Correct, sir. So, very, very rightly mentioned. So, depending on the dimension of the tube or the pipe, different tests can be performed. But what we are trying to see is that, is there a need of a test? Because if we know how the production was done, is there a possibility to predict which ones of this need an inspection or monitoring and which ones do not? So that not everything by default, we need to actually walk through the pipe and then find out if there is any kind of a defect or not. So because that is much more painful to do. So we are trying to restrict the number of those tests or minimize those tests by trying to estimate well in advance through in a mathematical manner.
Yeah, see, this pigging we do once in 10 years for one segment, okay?
Oh.
We don't do it regularly. It is once in 10 years. And that too, when we are doubt the wall thickness. Though we are having enough, factor of safety for wall thickness, this is a mandatory test prescribed to confirm, the fitness of the pipe. So pigging has to be done.
Okay, sir. Great. Yeah. Oh, yeah. You rightly mentioned it is oil and oil industry. So yeah, that's right. So there it is different. So I was just looking when we are actually producing the pipes or the tubes in the manufacturing plant. So that's where I was looking at. So in an oil sector, yeah, I completely understand. So this is already in a consumption environment, and then after it has been consumed, how do you still go ahead and discover what is the condition of those pipes? Yeah, got you, sir. Sir, I think
mic is mute, sir.
Any more questions from any other participants? Otherwise, we'll move on to the next agenda. So, Dr. Kevin is there? Dr. Kevin? Okay, thank you, madam. It was an excellent show by you. Really, it was a very good presentation. We had enjoyed your program and we learned a lot from you, from your presentation. Thank you so much for sparing your valuable time and experience with us. Really, it was an enjoyable one. Thank you so much. And looking forward to associate with you in future, near future. Thank you so much.
Oh, thank you.
Now, two more agendas. Just wait for a few minutes. Vote of thanks. And the next week program. Next week program is about that is next week Tuesday. That is a human value and insurance. There is a general talk. It is going to be delivered by Suresh and Shalini. That is both branch manager for Tata IEI for Trichy. It will be a general talk. Finally, they will tell about what is insurance plays in our role in a life like that. And moving on to the next agenda, there is vote of thanks. I call upon Dr. Dhanuskudi, our former secretary, honorary secretary, propose vote of thanks. I call upon Dr. Dhanuskudi. Dhanuskudi, sir, over to Dhanuskudi. Dr. Dhanuskudi, sir. Hello?
Hello.
Yes,
Hello.
sir. Yes, sir. Please, sir. Please.
Good evening to all participants. Hello.
You are audible, sir. Please go ahead.
Okay. Good evening to all the participants. Today we had a very interesting lecture delivered by Dr. Sheila Siddhafa. principal data scientist and data and AI services unit from Bangalore. The topic today is manufacturing process inspection. She has very nicely delivered and brought out what are different types of data and what frequency data are collected and what are not what are to be not considered. Say certain data maybe in a graphical form with too much frequency, bulk data like that. So what will be a useful data and how the domain knowledge could be used to by AI or artificial intelligence for process inspection or product inspection. So very nice deliverance. It shows her subject clarity and vast experience. So all the participants got benefited out of her presentation. On behalf of all the participants and the organizing institutions, like Institution of Engineers, Tiruchirappalli Local Center, Computer Society of India, Trichy, and IIW Tiruchirappalli Center, IWS Southern Zone, IIM Trichy, and Industrial Engineers Tiruchirappalli, and non-destructive testing in society, and Kumari Arivial Peravai. So all these organizing, on behalf of all these organizing committees and also on behalf of all the participants, I thank Dr. Sheila Siddhafa for sparing her valuable time for the benefit of our members. Thank you, madam. Thank you for your presence and sharing your knowledge. Thank you.
Sir. Thank you. It was amazing discussion also. Very wonderful questions from the team. So I also really liked to such wonderful audience. Thank you.
Okay, thank you. I thank all the participants for being with us and making the event as a useful one. Thank you. Thanks to everyone.
Thank you, Dr. Dhanushkodi, for excellent vote of thanks. Thank you, madam, for your presence today. Really enjoyed your program. Thank you so much. Looking forward to associate with in future. Thank you so much. Good night to everyone. With your permission, we'll close the program, madam. Thank you.
Sure.
I wish all the members good night. Thank you so much for participating today. Thank you so much.
Thank you, sir.
Thank you.